I will present today the work of my team on EEG and fMRI neurofeedback integration for stroke rehabilitation. This is a context slide that shows you the paradigm of this project. So if on one hand we want to exploit neuroimaging tools and data processing techniques to provide rehabilitation solution for a wide range of brain disorders within the framework of neurofeedback. On the other hand, the challenge is also to exploit these multimodal brain measurements to learn a brain state model able to improve the quality of the feedback and also to improve its feasibility. During this presentation, I will briefly cover both aspects of these two lines of research with a focus on clinical application of stroke. So stroke is a global, serious healthcare problem, and it's the leading cause of disability worldwide. And if many interventions for rehabilitation are available, traditional solutions such as physiotherapy or robotic-assisted physiotherapy presents limitation, and in most cases patients show very poor recovery outcomes after 1 year from the stroke episode. Literature on stroke rehabilitation suggests that recovery is crucially linked to the process of relearning new patterns of activation that specifically involves preserved brain areas that have been spared from the stroke episode. And on these premises, as also recent studies have shown, a neurofeedback or a BCI solution have great potential to really promote plasticity and reorganization of perirelational areas. Current approach on stroke rehabilitation using neurofeedback or BCI relies on unimodal modalities. So historically, they have used the EEG because of its affordability and also because it allows for numerous training sessions, which may be important, may be crucial for the process of learning. However, as we've seen it today, neurofeedback or BCI training with EEG is strongly limited in its specificity because of the low spatial resolution of EEG. On the other hand, recent works have used fMRI or neurofeedback for stroke rehabilitation, for motor recovery, and have shown that this modality is able to provide really high quality rehabilitation by identifying the specific cortical targets. However, because of the cost and of this technology and the accessibility of this technology, the number of sessions per patient that we can perform is severely limited. I don't need to go much through this because Jersey did it excellently before, but I think this slide summarizes a bit all the imaging techniques we've seen today, and also shows that EEG and fMRI not only have a high degree of complementary from the spatial and temporal resolution point of view and from the practicability aspect, but they also are sensitive, they also grasp two different aspects of the brain activation. And I think this is an important point to underline. EEG is being sensitive to the electrophysiological response of neural activation after a stimulus, and fMRI measuring the hemodynamic response, therefore the metabolic demand of brain activation. So combining these two different information, we can we can provide the subject or the patient richer information about his brain activity, and these are potential to achieve a more specific and efficient neurofeedback. So this was the starting point of our research project, which aims at to make full and enhanced use of the neurofeedback paradigm for brain self-regulation in motor and psychiatric disorders. As we've seen, however, integrating EEG and fMRI for real-time neurofeedback is quite challenging. So the first years of this research were devoted to the design and implementation of a bimodal neurofeedback platform. This platform was then tested on a population of healthy volunteers, and only recently we've extended the paradigm for stroke rehabilitation. So here is a schematic of the platform, which is in place at the University Hospital of Rennes. We have an fMRI and EEG unit, the former using a 3 Tesla scanner, and the second using a 64-channel MR compatible solution. Those two data acquisition units are linked to the neurofeedback control unit, which is responsible for data stream synchronization, signal pre-processing, neurofeedback computation, and visualization by means of a screen inside the MR bore. And this is just to show you, to give you an idea of the complexity of such a system. Here you see synchronization and control paths. And if you want more technical details about the implementation, you can check the paper from Marcel Manot. So this platform actually is performing bimodal neurofeedback with an grade rate of 1 second for the fMRI neurofeedback score and 250 milliseconds for the EEG. So this, as I mentioned before, the first step was to test the platform on a population of healthy volunteers. So we did so on 30 subjects and in 2 studies. So the first one was a proof of concept study aiming at show feasibility of bimodal neurofeedback for a motor task, and also to investigate its efficacy with respect to the unimodal solutions. So this study showed that simultaneous EEG fMRI neurofeedback provide stronger and more widespread activation for a motor imagery task, as we see here, than unimodal solution. So on EEG neurofeedback only or fMRI neurofeedback only. We also investigated in a second study the 2 different types of neurofeedback metaphor, a bidimensional one where EEG and fMRI could be controlled separately, and a unidimensional one where the neurofeedback score was the result of the average of the 2 neurofeedback score, EEG and fMRI. And we found out that while the former is more engaging for the subject, the last one may be easier to control. So we decided to use this one for the pilot study on stroke patients. This study involved 4 chronic stroke patients with upper limb hemiparesis. The neurofeedback protocol is shown here, and it consists of an alternation of bimodal neurofeedback sessions and unimodal EEG-only neurofeedback sessions. Here the hypothesis was that the patient could develop a strategy for motor imagery during the bimodal session because it was receiving richer information from EEG and fMRI, and then hopefully transfer this strategy to the unimodal session. In order to, let's say, guarantee a sufficient number of training. So this pilot aim was to test feasibility of the paradigm on stroke patient, which was not evident, but also to identify critical issues for the design of a larger cohort study. With this slide, I summarize the methodologies regarding calibration. So before each training session, patients were performing motor imagery without feedback, and data collected in this calibration session were used to estimate an optimal common spatial pattern filter over the motor electrodes for the EEG score. And also to estimate optimal region of interest for the fMRI. Regarding the choice of the cortical target, we know that it is always a crucial point when designing a neurofeedback protocol. In case of stroke rehabilitation, literature suggests that primary motor area can be the best target for recovery. I showed it in red here. However, for more severely affected patients, supplementary motor area may be a useful alternate to the primary motor area because it's easier to activate for a motor imagery task. So on these premises, we proposed a multi-target dynamic training strategy that more strongly rewarded activity from the supplementary motor area at the beginning of the training, and then increased the contribution of the primary motor area in the final session. And here I show some results for a patient that performed particularly well. So here are neurofeedback trends over the 3 rounds of neurofeedback training. The relative supplementary motor area and the primary motor area activation, and also the bold activation maps for the first session in orange, and for the last one in green. So results show that this patient significantly upregulated activity in the ipsilateral motor cortex and exhibited very regular neurofeedback trends in the last session. Results from the EEG part show that there was a positive activation of ipsilateral motor electrodes in the unimodal session, while in the bimodal one, the amplitude of the event-related desynchronization is smaller. This is a well-known limitation of EEG acquired under fMRI, and also for the healthy subject study with similar results. And these are results for the 4 patients included in the study. So here we have a clinical score assessed with a Fagel-Meyer score, and also fMRI neurofeedback score in this last column. 3 out of 4 patients managed to significantly upregulate activity in the ipsilateral motor area, and more importantly, 2 of them had a significant improvement of the motor skills of the affected limb. This is quite encouraging if we consider that those patients were chronic patient, therefore at more than 1 year from the stroke episode, and for them any spontaneous recovery is expected. So this pilot study, this proof of concept study, was useful also to design the protocol for a larger cohort randomized controlled trials that we are currently performing, that will involve 2 groups. an interventional one, and a control group that will perform only motor imagery. The protocol will last over 5 weeks, so it's quite a demanding study, and that deploys lots of resources, and I think it's an important point to underline. So fMRI neurofeedback clinical applications are very limited by this, by the cost and the resources. And this brings me to the last part of this presentation, where I want to briefly mention, because I'm running out of time, a parallel act of research where we want to reduce the use of fMRI while keeping the quality of the bimodal neurofeedback sessions. And we do so proposing a model able to imitate the bimodal neurofeedback scores using EEG only. This model is based on a nonlinear regression with sparse regularization, and its results on 17 subjects show that it is able to improve the quality of the neurofeedback based on EEG only. Here I show an example of this. Is in purple the trends for the bimodal neurofeedback score, and in green its estimation using the model, and therefore only EEG signal. If you want to know more about this, you can check out the e-poster of my colleague Claire Curie. I would like to thank you for your attention, and also acknowledge the work of my colleagues for that contributed to this project, and also in the preparation of this talk.